Hi everyone, welcome to my presentation on moving iron instruments. In this presentation, we are going to see the construction and working of moving iron instruments in detail. I am Swati Polasa, lecturer in Electrical and Electronics Engineering, Sanjay Gandhi Government Polytechnic, Adilabad. Getting inside, let us see the types of moving iron instruments. Moving iron or MI instruments can be classified as attraction type moving iron instruments and repulsion type moving iron instruments. So we are going to have either attraction type or repulsion type moving iron instruments. Let us try to understand the principle of working of moving iron instruments. Generally, when an iron piece is placed near a magnet, it gets attracted towards a magnet. That's it. It's a very simple principle of working. We'll have a magnet, magnetic field, a magnet. Then we'll have an iron piece. Depending on the strength of the magnetic field, iron piece will get attracted towards the magnet. So the force of attraction depends on the strength of the magnetic field. So here it is very clear that for a moving iron instrument, we need to have some magnetic field or a magnet, and we need to have a soft iron piece. Because iron piece is a ferromagnetic material, it will get attracted to the magnet. Let us discuss about the construction of attraction type MI instrument. So we are getting into attraction type MI instrument. We have already discussed that we can have two types of MI instruments. One is attraction type MI instrument and another one is repulsion type MI instruments. So now we are going to discuss about the construction of attraction type MI instrument. The attraction type MI instrument works on the attraction of iron vein into a coil carrying current to be measured. So we are going to have a coil, and this coil will be carrying current to be measured, and then we need a soft iron piece. So for that we will use an iron vein, and that iron vein will get attracted to the coil which carries current. Why? Because coil carrying current produces magnetic field. A soft iron vein is attached to the moving system. That means coil is going to be a stationary system here. In PMMC instrument, coil was moving, but in MI instrument, coil will be stationary, it will be carrying current, and because of the current carrying conductor, there will be magnetic field. That means an electromagnetic field is produced, and we have iron vein which is attached to the moving system, and that iron vein experiences force of attraction towards the magnetic field. So here iron piece is moving, and hence the name of the instrument is moving iron instrument, and this iron piece is getting attracted to the magnetic field, hence the name is attraction type MI instrument. So then the current to be measured is passed through the coil, a magnetic field is produced as we have discussed just now. Let us see an image of MI instrument. So here you can see there is a coil. This is a cross-section view of a coil. So this is a section, full section. So here you will have conductors. Here you will have conductors. So we are going to have conductors making a coil, and we have spindle here. This is a spindle. Over the spindle, we have a pointer, and we have another attachment to the spindle. This is for damping. So here MI instrument uses air friction damping. And in this image, we see that the controlling is with the help of control weights. We can have gravity control or spring control for MI system, MI instruments. We can see that there is a balance weight. This balance weight is trying to balance the weight of the air, damping chamber, as well as the pointer. And we have seen the coil. This is the coil. This should be our cylindrical coil. If we check out for the plan of this coil, this is the axis of the cylinder. This will be the plan of the coil. So our this will be the coil, this will be the cylinder, and inside we are going to have coil. Like this, we are going to have coils inside. We'll just wound the coils. Coil will be having two ends. And once you just wound the coils, you will have two ends of the coil coming out. And here we are going to give the current. So this is the plan, and this is the sectional view of MI instrument. So you can see, I'm just trying to, and in us is this one. So coil that is brown. So here in this gap, you will have coil placed. This field attracts the eccentrically mounted vane on the spindle towards it. So you can see when current is flowing through the coil, there will be magnetic field produced. So electromagnetic field is produced here, and this moving vane experiences its force as shown in the figure. So this is the vane, iron piece, and it is experiencing force of attraction towards the magnetic field, and hence the pointer will be moving clockwise direction. The field attracts eccentrically mounted vane on the spindle towards it. Here it says that the vane is eccentrically mounted because it's not centered inside the coil, it is centered outside the coil, and hence it's eccentrically. Now the spindle is supported at two ends on a pair of jewel bearings, so same pivot jewel bearing system, and thus the pointer which is attached to the spindle is moving of the moving system is deflected. The pointer moves over the calibrated scale. This pointer will be moving over the calibrated scale. So it is very simple. You have eccentrically mounted a vane, and that is mounted on a spindle which is carried by pivot jewel bearing system. And when coil is excited by current, you will have electromagnetic field produced, and the soft iron piece get attracted towards the electromagnetic field. Hence there will be force of attraction towards this direction, which will move the pointer in a clockwise direction, and pointer is made to move over a calibrated scale, and hence the deflection is produced. Now we need a controlling torque. Controlling torque can be given either by control weight or control spring. And then we have damping torque. Damping torque is provided by air damping chamber. Before discussing about this air damping chamber and a control of the moving iron instrument, we will have another view of same MI instrument, especially on the coil, on the vane. Let us see. Here, this image clearly explains. This is the coil. We have two ends of the coil here. This is eccentrically mounted. It is not inside the coil, hence it is called as eccentrically mounted. This is the vane, and vane is attached to the spindle, and spindle is connected to the pointer. Pointer is attached to the spindle, and we have damping piston. This is the damping system. Inside the damping system, you are going to have a piston here. This is air dashpot or air chamber, and we have counterweights here in order to balance this. Otherwise, there will be gravity pull which will be helping the movement of the piston inside the air chamber. So in order to balance that weight, we have balancing weights here. Now, if current is flowing into if current is flowing inside this manner, there will be electromagnetic field produced. Say in this manner. That means here we have north pole created, and here we have south pole created, and ultimately we have magnetic field produced here, and this iron piece will get attracted to the magnetic field. So there will be force of attraction on this. So when it is moving, everything is rigidly attached. So your pointer will try to move clockwise, and also our pointer moves clockwise. It will be moving on a calibrated scale like 0, 1, 2, like that. And we have another one which is attached to the spindle, and that is our damping. And you have dashpotting. This is air dashpot or air chamber. Inside that air chamber, you will be having a piston here, say. Now, because there is a force this way, that means spindle is trying to move in clockwise direction, your piston should be experiencing a force as mentioned here. So while doing that, there will be difference in pressures, which is trying to oppose the free movement of the spindle, and hence damping torque is produced. Let me come again. This is a coil, and if coil carries current, there will be electromagnetic field produced. and the iron piece, being a ferromagnetic material, it will get attracted towards the magnetic field, and there are many things attached to the spindle. One is pointer, another one is vane, which is iron vane, and another one is a piston inside air chamber. There is a counterweight which balances the weight of the piston, and of course there will be a control system. The control torque may be produced by either gravity control or a spring control. Here we can have spring control, and that is the reason why gravity weights are not attached. And now when vane is getting attracted towards the coil, the whole system or spindle will try to move in a clockwise direction. In a clockwise direction means pointer will also move in clockwise direction. Dashpot will also move in the dashpot. We have piston inside, and that piston will also try to move in a clockwise direction. When it is trying to move in a clockwise direction, the piston is coming out. It is trying to come out of the dashpot. The piston movement is in air chamber, so it is not that easy that piston is held freely to move in air chamber. There will be differences in pressures which will try to oppose the motion of the piston inside the air chamber. Then those forces are very less, which are sufficient to provide damping of the oscillations of the pointer. Same thing is mentioned here. If the current in the fixed coil is reversed. So let us see what happens if the current in the fixed coil is reversed. What happens? Earlier we have seen left side we had north pole and right side we had south pole. When current in the coil is reversed, we'll have reverse magnetic field. So right side will have north pole, left side will have south pole. Whatever might be the poles, you are going to have a magnetic field, and we are not having another magnet that it repels or attracts, but we have a simple soft iron piece which gets attracted towards the magnetic field. So even though the field of the when the current is in the coil is reversed, the field produced by it also reverses. So the polarity induced on the vanes reverses. The polarity induced in the vane reverses. Thus, again, then you will have soft iron piece getting attracted towards the magnet. Thus, whatever be the direction of the current in the coil, the vane is always demagnetized in such a way that it attracted into the coil. So the eccentrically mounted vane will get attracted and it will be attracted into the coil. Hence, such instruments can measure both DC as well as AC. So, MI instruments, here we are talking about this attraction type. It can measure both AC as well as DC currents. We will discuss a small concept here. So, when we had North Pole here, say, and South Pole here, that means magnetic field will be in this manner. Now what happens is, this iron vane will be having inner molecular magnets because it's a ferromagnetic material. It will be having inner molecular magnets arranged in random fashion. But when it is placed in a magnetic field like this, so here we'll have south pole and here we'll have north pole. The molecular magnets are arranged in this fashion. South, north, south, north, like this. And Now this south pole will get attracted to this north pole, and hence this piece will get attracted towards this coil. So this is what is going to happen. So your vein, being the ferromagnetic material, can be assumed to have molecular magnets which are arranged in random fashion. But when the vein is placed in a magnetic field, depending on the magnetic field, there will be alignment of these molecular magnets in such a manner that here you can see we had a north pole. Field will be magnetic field. Actually, it should pass through because permeability of the soft iron material is high. Magnetic field should be passing through. Then if you check out, I'll just draw the magnetic lines of force. It is supposed to be like this. Completing, I'm just trying to draw only one flux line. Now here, when I say that magnetic line of force is leaving from this side and it is entering from this side, that means here we had north pole and here we had south pole. Now coming to this soft iron piece, now what is happening is molecular magnets are getting aligned in proper manner. So you just imagine that, say we had a molecular magnets arranged in a very good manner. Now if I consider this hole as a portion of a magnet, and there is a magnetic field here leaving and there is a magnetic field here entering, which means if I consider this as some other magnetic field should be leaving from north pole and should be entering into south pole outside the magnet. Inside the magnet, magnetic lines of force should be flowing from south to north, outside from north to south. So hence here this side we have south pole and this side will be having north pole, and south pole will get attracted to the north pole of the main magnet field, and hence your vein gets attracted. So this is the important concept you should understand. So if polarity is reversed, here if it was south pole and here it is north pole, then here we will have north pole. Again you will have unlike poles on both the sides. Again, then also your soft iron piece will get attracted towards the magnetic field. Hence, these MI instruments are useful for both AC and DC measurements. So the control torque is provided by two hairsprings S1 and S2, as in the same way we have used in PMMC. But in PMMC, those two springs were carrying current. Here, we don't require any flow of current into the vein. So we don't require any current inflow inside the moving system. Our moving system is simple. It carries only a simple vein. So this is robust. We can handle it easily. We have learned that PMMC must be handled in a sensitive manner, not in a rough manner, otherwise it gets damaged, because moving system carries coil and there are soft, delicate joints between coil and a spring and all. Hence it should be handled with care. But in MI instrument, it simply, the moving system simply carries an iron vein. So simple in construction. Your stationary system is having just a coil, so no problem. Coming to the control, we can also have gravity control if you want the MI meters to be vertically mounted. So gravity control can also be used for vertically mounted panel type MI meters. Otherwise, we can go for spring control. Now, damping in MI instrument is air friction damping, as we have seen earlier. So, air friction damping is also called as pneumatic damping. Now, we'll get into the details of another type of MI instrument, which is repulsion type MI instrument. The principle of working of repulsion type MI instruments is unlike poles attract each other and like poles repel each other. So here we are going to have like poles and those two like poles will get repelled each other and hence we have some kind of deflecting torque produced. So this moving irons instruments, we can have two different designs for moving iron instruments which are commonly used, and those are radial vane type, which are more sensitive compared to coaxial vane type. So radial vane type and coaxial vane type MI instruments. Out of these both, radial vane type is more widely used because of its sensitivity. We'll have a picture about a radial vane type MI instrument. This is a repulsion type moving iron instrument. In this repulsion type moving iron instrument, again we have a coil. This is a coil. Coil is stationary, and to this stationary coil you can see that there is a vane attached. So we have a coil wound here, and to this coil we have a vane attached. I think everybody is able to see this vane. So you can see this is vane. So let me call it as a fixed vane. So this is a fixed vane, and we can see that at the center of the coil we have spindle, and to the spindle we have another attachment of the vane. Here we have another vane which is attached to the spindle. You can see this vane is attached to the spindle. This is the spindle. This is moving vane. Moving vane, fixed vane, and this is spindle. So this is a coil, this is a spindle. Spindle is attached to a moving vane. We have fixed coil arrangement, and we have another vane attached to this fixed coil. This is the attachment of fixed coil. This is the attachment of the moving coil. So we can see that one vane is fixed and another vane is moving. Let us see what happens. Now, say there is a current flowing in the coil. We have current flowing in the coil, and because of this current flow, say we have north pole created on this side, south pole created on this side. This is north pole and this is south pole. Okay. Let me draw the lines of force here. So you'll be having lines of force in this manner. Magnetic lines of force. We have lot many. I'm just drawing two. Now for this lines of force, we'll be having here also. We'll be having here also. Then, as we have discussed here, we had North Pole and we had South Pole. Inside this vein, your magnetic lines of force will be in this manner. When it is in this manner, here also you'll be having magnetic lines of force in this manner. Now, your vein is trying to get magnetized when it is placed in a magnetic field, as we have discussed earlier. That means there will be molecular magnets arranged inside, and when they are arranged inside, they'll be arranged in what manner? Here you have North Pole, and bottom side you will be having South Pole. You cannot see complete bottom of the vein, so I'll just write NF, which states the polarity of the fixed vein, and this will be SF. SF will be somewhere down there. If here is NF. And similarly, you will have magnetic lines of force for this moving vein. It is moving upwards. So here, outside the magnet, the lines of force is going to be like this manner. No? Here we had it in this manner. So it is going outside. So this is North Pole and entering into South Pole. Out North Pole and South Pole. Inside the magnet, it will be flowing from north to south. So here also, inside the magnet, it will be flowing from, south to north. Outside the magnet, it will be flowing from north to south, which means that this should be north polarity of the moving coil, and somewhere down we'll be having south polarity of the moving coil. So this is the north pole of the fixed coil, south pole of the fixed coil. Because of the magnetic field set up by this north and by this moving coil, what is happening inside this fixed vein and what is happening inside the moving vein, we are seeing. So we can see that north pole of the fixed vein is here, and south pole of the fixed vein will be somewhere bottom. Similarly, we'll have north pole of moving vein up and south pole of the moving vein bottom. Now, what happens is, when you have this spindle arrangement near to the fixed, because this is fixed, say spindle position was in such a manner that both are very near or together, very close to each other, then if you give current, then what happens is the magnetic fields are produced in such a manner that there are like poles near each other, and hence there will be force of repulsion between these poles. That means there will be force in, as I have shown, because this is fixed vein, it cannot move, and hence because of the force of repulsion, you will have only moving vein moving away from the fixed vein. So our spindle will be having zero position when the moving vein is very close to fixed vein. And when you give current, then your moving vein will move away from the fixed vein, because we have like poles created in the veins and like poles to repel, and hence the force of repulsion affects the position of the moving vein. It cannot affect the position of the fixed vein because it is fixed. Moving coil is stationary. Hence, your moving vein will be moving, and along with the moving vein, spindle will be moving, and hence this pointer will move from zero position to some other position where the deflecting torque is equal to controlling torque. Hope you're clear with the explanation of this. And this is the construction, simple construction of moving iron system. Here we have two veins directly. Now if current is reversed, everything will be reversed. Here you will have south pole, here you will have north pole, and this will be south instead of north, this will be south instead of north, this will be north instead of south, this will be north instead of south. And of course, this field direction will get reversed. That is the reason why you'll have south at the top, north at the bottom. Again, you'll have like poles. So again, there will be force of repulsion, and hence the moving coil will move. In this type of vein, the veins are radial strips of iron The strips are placed within the coil. As we have seen the construction, I'm just running through it quickly. The fixed vane is attached to the coil and the movable one to the spindle of the instrument. The instrument pointer is attached to the moving vane spindle. As current flows through the coil, the generated magnetic field induces identical polarity on both the fixed and moving vane, and hence, thus, even when current through coils is reversed, there will always be force of repulsion acting between like poles of fixed and moving vane. Hence, deflection of the pointer is always in the same direction, irrespective of polarity of the current in the coil. So, though it is one direction current or it is in reverse direction of the current, your vanes having same polarity and there is force of repulsion. So the direction of motion of the pointer is same for the positive half cycle of the current as well as negative half cycle of the current. Hence, MI instrument, both attraction type or repulsion type, can be used for measurement of AC currents also. The control and damping torque in a repulsion type MI instruments. The control torque is provided by two hairsprings S1 and S2 in the same way as PMMC. But in PMMC, it's again the same old story. We can also have gravity for vertically mounted MI types, and the damping torque is provided by a thin vane in a closed sector shaped box or simply by a vane attached to the moving system. So here at the bottom, let me draw it here. Here we can have a simple vane like this. We can have a simple vane like this. Okay. Now when this vane is placed in an iron chamber, air chamber. This is our air chamber. Now when it is moving, because this vane is moving inside the air chamber, it cannot move that freely for the oscillations, and it can easily dampen the oscillations of the pointer. Okay, like this we have, so this inside this we have air, and this is our vane which is attached to the pointer spindle. As moving system moves, this vane inside the air chamber should also move. Now, when TC is equals to TD and pointer is facing some oscillations, that oscillations are opposed by this vane. We can see the picture of a coaxial vane type. Principle of operation is the same. Concept is same. You have a coil here, section view you can see. We have a coil here. We have a strip coaxial vane. This is, we have a sector shape strip here and also a small sector shape vane here attached to the spindle. Small sector shaped vane. You can see the movable vane shape. It is sector shape, and we have, you can see kind of an arc picture here. And we have a sector shaped vane attached to the cylinder here. This cylinder is a cylinder on which we have coil wound. Now what happens when you give current through this? The polarity of the vanes will be same. and hence this movable vein will get repelled away from the fixed vein. That's all. So this is moderately sensitive compared to radial vein type. So we'll look into the deflection torque of MI instruments. From moving iron instruments, how we are going to have deflection torque. This can be derived by taking energy relation into consideration. So energy relation can be considered for small increment of current supplied to the instrument. This result in small deflection. Say there is small change in current supplied to the instrument. Say it is DI. Because of DI, small change in current, you will be having change in deflection. You will be having change in deflection. So we are saying that there is a small change in current. So we are discussing about DI. Because of change in current, we'll be having d theta, and that means there is some mechanical work done here, and the mechanical work done is torque into uh, change in angle, which is mentioned here. It will be a torque because of which the moving system is moving, that is TD, and how much it has moved, that will be d theta. So TD into d theta is the mechanical work done. And if I be the initial current, L be the inductance of the instrument, and theta is the deflection of the instrument, we can have some other equations like this. Say phi is the flux produced because of the current through the magnetic coil, and flux is nothing but inductance into I, so L into I. Rate of change of flux is the applied voltage. So that means when you apply certain voltage, this will be the rate of change of flux. So d by dt into L into I. So it's going to be I dl by dt plus L di by dt. Now E I dt. We are trying to get the value of E I dt. That means on both the sides, forget about this one. E is equals to I dl by dt plus L di by dt. On this side and on this side, that means on both the sides of this equation, we are multiplying I dt. So here it is going to be E I dt, and here it is going to be I square, dt dt gets cancelled, so dl, and Li di. I'll just write the same. So we had E is equals to I dl by dt plus L di by dt. So on both the sides, we are trying to multiply with I dt into E is equals to, so it will get distributed here. So I dt into, we already have I here, into dl by dt. Plus we have another term IDT, I am multiplying it with IDT again. So L di by dt. You will have dt getting cancelled here and here. So we will have so EI dt, which is mentioned here, EI dt is equals to I into I square dt got cancelled. So we are left out with dl. So dl, I square dl plus il di. That's how we arrive into this equation. So what is this ei dt? Ei dt is nothing but electrical energy supplied. Yeah. So ei is power. Power into dt should give you energy. So this is the electrical energy. That is the reason why we are multiplying by, on both the sides by I dt. So that we get energy which is supplied. Electrical energy supplied. Now the current is changing. It changes from I to I plus di, because we have already said that but some change in current I, there is some change in theta. The change in current is di and change in deflection is d theta. Initial value of the current is I. So I is changing from I to I plus di. Di is infinitesimal change in current. So final value will be initial value plus change. So it is changed from, the current is changing from I to I plus di. This is the final value. Similarly, the inductor value also is changing from L to L plus DL. This DL is infinitesimal change in inductance. Therefore, what happens? There will be stored energy changes in inductor. We know that inductor will store electrical energy, and what is that stored value? It's half Li square. So initially it was half Li square. From half Li square, it has changed to half. Instead of I plus di whole square. Instead of L, we have L plus di. Hence, the change in stored energy will be this minus this. So you have final energy stored minus initial energy stored. In here, you will have the difference, change in energy stored. We are seeing all changes here. So we'll see now why did we calculate the mechanical work done, and we have calculated electrical energy supplied to, and then we have calculated increase in stored energy. Why is here the reason? The principle of conservation of energy, law of conservation of energy says that energy is neither created nor destroyed. It simply changes its form. Now, for the MI instrument, we are supplying it with electrical energy. That means electrical energy is supplied. And we had an equation for electrical energy. That is, this is the electrical energy supplied. I've already derived it. I square dl plus I, dl by di, dl di, I square dl plus IL di. This is the electrical energy supply. When you give electrical energy, what is happening inside? There is some energy stored. Why? Because we have inductor coil. It will be storing energy. So there is some energy stored. And rest of the energy is converting this electrical energy to mechanical energy. So there is some mechanical work done. You had repulsion force or attraction force of the vanes, and there is some mechanical work done, and that is PD into d theta. So what we have is mechanical work done. So if you put this in mathematical equation, then you have electrical energy supplied, which is already calculated, is equals to increase in stored energy. This is increase in stored energy plus mechanical work done. TD d theta is the mechanical work done. if you just simplify it, we want TD d theta. You can see I have I square dl and I have half I square dl. So if I send this half I square dl this side, I'll be left out with half I square dl, and we have ILDI on both sides. This will get cancelled out. So you'll have ILDI getting cancelled, and here for simplifying these two, you'll be left out with half I square dl on this side, and this side will be having TD d theta. So this is the simplified form after using the law of conservation of energy and simplifying the mathematical equation. So TD d theta is equals to half I square dl. That means deflecting torque is half I square dl. If you see, for PMMC, TD was directly proportional to I. But for MI instruments, the deflection torque is proportional to square of current. It is not proportional to I directly, it is proportional to square of current, which clearly states that our scale is not going to be uniform anyway. That means if we have seen that in the last session, last presentation for PMMC instruments, we had linear scale, uniform scale. Uniform scale, why uniform scale? Because TD was proportional to theta, as when we use controlling torque as spring control. But for gravity control, again, it will be sine scale. But for spring control, it was a uniform scale. But coming to MI instruments, our TD itself is not proportional to I, but it is proportional to I square. And let us see what happens for a spring control MI instruments. Now for a spring control MI instruments, for the pointer to come to a steady position, the controlling torque should be equal to the deflecting torque. And for that, controlling torque is K into theta for spring control, and deflecting torque is half I square dl by d theta, that we have derived it, which means theta is equals to half I square by some constant, that is spring constant, into dl by d theta. This is the formula for the deflection. So we have seen the derivation of this deflection torque and how deflection is related to the quantity which we are trying to measure. We have seen that it is like a square of the current. So deflection is proportional to square of the current. So deflection is proportional to square of the current. That means scale is not uniform. The moving iron instrument have their deflection which is proportional to square of the current flowing through the coil. These instruments are thus said to follow square law response and have non-uniform scale. I have placed an image of an MI instrument. You can see the meaning of non-uniform scale. See, here we have a pointer and you can see the symbol here. This symbol mentions that it is an MI instrument, and you can also see that it is varying from 0, 100, 200, 300, 400 and 500. Now at beginning the readings are crowded, they are very near to each other, cramped, and later on from 100 to 200 it is a bit having more angular distance, and from 200 to 300 even more angular distance. Again from 300 to 400 it is near, and from 400 to 500 it is near. So not that the angular distance from 0 to 100, 100 to 200, 200 to 300, 300 to 400, 400 to 500, it is not same at all. This means that it is a non-uniform scale. This is because angle of deflection is proportional to square of current, not directly to current as in PMMC, even though the control is spring control. Okay. I hope you understood the construction and working principle of attraction type and repulsion type moving iron instruments, and the learning outcomes which are expected from this presentation. After listening to this presentation, the student should be able to describe the construction and working of MI system, MI instruments, both attraction type as well as repulsion type. Hope you have understood the concepts explained in this presentation. Thank you.